In this video, we're going to start talking about continuous probability theory. We've been talking about discrete probability for a while now. So for discrete probability, well, discrete just means you can list all the possible outcomes. So we had some x is the set of all outcomes, and probability just meant you have some function on x. It spits out, if you put in an outcome, it gives you the probability of that outcome. And really the only thing that has to happen, well, the probability that something happens is equal to 1. So if you add up the probabilities of all the possible outcomes, you better get 1. So we saw lots of examples of this. So say if you flip a coin, well, in this case your x is either heads or tails, and the probability of both of them is 1/2. Another example, if you roll 2 dice, well, this is a little different than the last one because you can get anything from a 2 up to a 12, but the probabilities are not all the same. We saw that, well, the only way to get a 2 is if you roll 1, 1, so the probability is 1 in 36. For a 3, though, you could get either a 1, 2 or a 2, 1, so the probability is 2 in 36. And yada yada. It keeps getting bigger till you get up to 7, which is 6 in 36. And then it starts getting smaller again until you get to 12 is 1 in 36. So this was a couple examples of discrete probability distributions. But now we want to start talking about what happens if you have continuous probability. So again, continuous means it is impossible to list all the outcomes, which at least makes it seem a little unlikely that you can just go one by one naming what the probability of all the outcomes are. So let's take an example. Let's say we're going to throw darts at a dartboard. So here's my dartboard. And I want to know what's the probability that I score a perfect bullseye. Well, the probability of a perfect bullseye, I mean, perfect means if I'm off by a fraction of 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 an inch, that I missed. There's no way I could possibly hit this perfectly dead center, no matter how many times I threw the dart. So the probability of a perfect bullseye is 0. Well, what if I make my condition a little less stringent? Instead of a perfect bullseye, I'm just going to put a little circle in the center and say, what's the probability of a near bullseye? Well, this one I can actually do because I don't have to hit one specific spot. I've got a little area to work with. And you can probably guess what the answer is going to be. It's the area of this circle that I'm wanting to hit in divided by the area of the whole board. Of course, really that would be if I was just randomly throwing. I mean, in real life I'm going to aim, so hopefully the probability is a little bit bigger than that. But I mean, you can imagine if you just stick a dart randomly somewhere on the board, the probability it's in the circle is just how big is the circle compared to how big is the board. And this winds up being a general theme in continuous probability. Pretty much no matter what situation you got, continuous probability always winds up being the area of something. Area of what is a good question. I mean, in this one, the example is pretty geometric itself, so it's not that hard to think of what area you're doing. in general, trying to figure out what the area that you're looking at is pretty tricky. But yeah, in this class, we're going to make our life a little easier. If you do general probability spaces, it winds up being very, very hard. So in this class, X is always just going to be the real numbers. To do that general one, just in case you want to hear the buzzword, there's a branch of math called measure theory. If you happen to want to go to grad school in math, this is probably a class you take your first year. To do probability for general spaces, for general continuous spaces, you need measure theory. There's no way around it, and it's really tricky. I'll make a video at some point kind of showing a little bit of the issues you run into, but let me just say for now it's beyond the scope of this course. So for this class, again, X is always going to be the real numbers. And, well, instead of actually having a probability distribution, we're going to work with something called a probability density. And it's kind of like what we had before, so probability density is going to be a function on R. This time it doesn't have to go to numbers between 0 and 1, it just has to go to positive numbers. And the probability of any particular outcome, well, what it is you draw the graph of P, and then it's the area under the graph between the 2 points you want. So this sounds kind of complicated, but it's really not. Well, let's draw a couple examples and it'll make a whole lot of sense. So let's start out with something simple. Let's say our P is, well, let's make it uniform. We'll say that no matter what, we know our X is somewhere between 3 and 10, and the probability, we want it to be the same all the way across. Well, we know the probability of this whole area needs to be 1, which means this height here, well, since the bottom's 7, the height had better be 1/7. So our P is going to be 1/7 if X is between 3 and 10, and it's going to be 0 for any other X. Okay. What if we wanted to know what's the probability that X is not just between 3 and 10, let's say it's between 4 and 7. Well, this probability density function means you just go from the numbers you want, so probability X is between 4 and 7 is going to be start at 4, end at 7, draw you a little box under your curve. It's whatever the area of that box is. Well, again, the height of this whole box is still 1/7. The base here from 4 to 7 is 3, so this would be 3/7. All right. In general, let me draw just kind of a generic P to show you if P looks something strange like then if I've got, okay, so say from 2 to 5, the probability that X is between 2 and 5 is just start at 2, go to 5, and whatever this area is, that's your probability. If you've taken calculus before, you know there's a symbol for this, but if you haven't seen calculus before, don't worry about that. Alright, so that's what a probability distribution is, and for now let me just leave you with the most common one. So the normal distribution, which we've talked about several times already in this class. Let me just draw the picture of the function. It looks like that. Well, that's not just a great picture, but if you happen to care what the function is, it's 1 over square root of pi, e to the negative x squared. This distribution comes up a lot because we're going to have something later called the central limit theorem. Well, by later I mean at the end of this unit. Basically, the central limit theorem says if you start with any distribution whatsoever, and instead of looking at the distribution, if you look at its average and you take averages that are big enough, well, if you keep averaging things forever and ever and ever, eventually you just get a big hump in the middle. So it basically says everywhere you look, there is a normal distribution. It may not be the distribution you care about, but if you keep averaging that distribution over and over again, then you wind up with a normal distribution. So this guy is pretty key for doing anything in statistics, and we'll talk about him quite a bit.